In this video presentation, we will talk about the working principles behind the particle size analyzer, as well as the instrumentation, setup, calibration and measurement, maintenance and troubleshooting, and its applications to our society. So to begin with, a short introduction about particle size analyzer will be presented.
For our introduction, in a certain environment, it is desirable to measure micron-sized particles at high rates, to categorize the measured particles in accordance with their size, and provide an output that indicates the number of particles of each size that have been detected and measured. In the past, this result usually has been accomplished by pumping a sample into an instrument for analysis. The primary disadvantage of instrument requiring that a sample to be pumped into the instrument for analysis is their inability to measure particle size. This particle size examination is used to characterize the size distribution of particles in a given sample, which is applied to solid materials like suspensions. There are many different methods employed to measure particle size. Some particle sizing methods can be used for a wide range of sample, but some can only be used for specific applications. One basic problem in particle size analysis is characterizing particles using just one number. Particle size is an important attribute in active pharmaceutical ingredients, in solid oral drug products for manufacturing tablets and capsules, together with the sterile liquid products, that is, injectables.
Working principle: the equivalent sphere. There is only one shape that can be described by one unique number, and that is the sphere. If we say that we have a 50 microsphere, this describes it exactly. We cannot do the same even for a cube where 50 micro may refer to an edge or to a diagonal. With our matchbox, there are a number of properties of it that can be described by one number. For example, the weight is a single unique number as it is the volume and the surface area. So if we have a technique that measures the weight of the matchbox, we can then convert this weight into the weight of a sphere using the formula where r is the radius of the sphere and p is the density of that sphere. We measure some property of our particle and assume that this refers to a sphere, hence deriving our one unique number to describe our particle. This ensures that we do not have to describe our 3D particles with three or more numbers, which, although more accurate, is convenient for management purposes. Different techniques. Clearly, if we look at our particle under the microscope, we are looking at some 2D projections of it, and there are a number of diameters that we can measure to characterize our particle. If we take the maximum length of the particle and use this as our size, then we are really saying that our particle is a sphere of this maximum dimension. Hence, we must be aware that each characterization technique will measure a different property of a particle, and therefore will give a different answer from another technique which measures an alternative dimension. Each technique is not wrong. It is just that a different property of a particle is being measured. Thus, we can only seriously compare measurements on a powder by using the same technique. Figure 1 shows different answers possible for a grain of sand. Standards must be spherical for comparison between techniques. However, we can have a particle size standard for a particular technique, and this should allow comparison between instruments which use that technique.
For the principle of particle size measurement, the basis for nanoparticle size measurement is the phenomenon of Brownian motion. Brownian motion, also called Brownian movement, is any of various physical phenomena in which some quantity is constantly undergoing small, random fluctuations. It was named after the Scottish botanist Robert Brown, the first to study such fluctuations. Brownian motion, or the diffusion of particles, is inversely proportional to particle size, whereas large particles move slowly, while smaller particles diffuses faster. Also, temperature and viscosity of medium can affect Brownian motion, where higher temperature causes faster movement and higher viscosity reduces movement. Stokes-Einstein equation describes the relationship of this Brownian motion with respect to particle size, viscosity, and temperature. It is expressed in the equation d is equal to kt all over 3 pi times lowercase eta times d sub h, where d sub h is the hydrodynamic diameter measured in meters, k is the Boltzmann constant expressed in joules per Kelvin, T is the temperature expressed in Kelvin, lowercase eta is the solvent viscosity expressed in kilogram per meter second, and D as the diffusion coefficient expressed in meter square per second. For the principle of molecular weight measurement, it is possible to obtain the average molecular weight of a sample from light scattering measurement by using the Mark-Howick-Sakurada or MHS method. In the MHS method, diffusion coefficient can be obtained from dynamic light scattering, DLS for short, or photon correlation spectroscopy, PCS for short, and is expressed using the equation D is equal to K quantity MW raised to A, where D is the diffusion coefficient from DLS PCS, A and K are both constants, and MW is the diffusion average molecular weight. And lastly, for the principle of zeta potential measurement, zeta potential is related to particle mobility in the theory of electrophoresis. It can be measured using the laser Doppler electrophoresis, or LDE for short. Zeta potential is the potential difference between the bulk solution and the sliding layer or plane of ions loosely attracted to the charged particle. The zeta potential can be measured using the equation lowercase zeta is equal to 3 times u sub e times lowercase eta all over 2 epsilon f quantity Ka, where lowercase zeta is the zeta potential, u sub e is the electrophoretic mobility, lowercase eta is the viscosity of the solvent, epsilon is the dielectric constant of the solvent, F quantity Ka as Henry's function, where Ka is the ratio of particle radius to electrical double layer thickness, 1 over K as dBi length or electrical double layer thickness, and A as the particle radius.
Instrumentation. Two of the main types of particle size analyzers are dynamic light scattering and laser particle analyzers. Dynamic light scattering analyzers measure particles in solutions in the 0.6 nanometer to 6 micrometer range. Laser diffraction analyzers are used to particles in a material within the range of 10 nanometers to 3 millimeters, but we're going to focus on the laser diffraction system. A typical laser diffraction system is made up of three main elements: the optical bench, the sample dispersion units, and the instrument software. Optical bench. A dispersed sample passes through the measurement area of the optical bench, where a laser beam illuminates the particles. A series of detectors then accurately measure the intensity of light scattered by the particles within the sample over a wide range of angles. Sample dispersion units. Sample handling and dispersion are controlled by sample dispersion units designed to either measure the sample wet or dry. These ensure the particles are delivered to the measurement area of the optical bench at the correct concentration and in a suitable, stable state of dispersion. And the last one is the instrument software. The instrument software controls the system during the measurement process, and it analyzes the scattering data to calculate a particle size distribution. In more advanced instrumentation, it also provides both instant feedback during method development and expert advice on the quality of the results.
For the setup of the particle size analyzer, SZ100 Nanopartica, the unit comes with a kit consisting of 3 instruction manuals and also 3 general types of cells that will be used for the measurement. The first cell is used for determining the zeta potential. An indication is that it has 2 electrodes. The second one is a cell used for measuring the particle size, which is generally a single-use only cell. And if one wants to go for multiple usage, the third cell can be used with a made of glass.
For the calibration and measurement, laser diffraction analyzers and dynamic light scattering systems are based on first principles, so they are not calibrated, but rather are subjected to verification tests to assure system performance. A pass or fail criterion should be documented prior to the verification test, and a qualified person should be the one to test the system. If the system passes, it can then be used with reliability. However, if the system fails, the optics are first cleaned or adjusted and the system is tested again to make sure it can now be used in the analysis. The sample solution to be analyzed was first prepared, then the cell will now be placed into the sample holder of the device which is used for determining particle size. For the measurement proper, the software installed in the computer was clicked, where the appropriate measurement that is being done was selected, then the temperature was configured. Wait for the cell temperature being controlled until a change in color of the settings was indicated, which means that the temperature was now set. Next is setting the conditions, wherein you will now assign the sample information. After setting the sample information, the type of the sample, dispersion medium, and the refractive index will then be adjusted. For the measurement mode settings, you can adjust the number of measurements and the delay between the measurements. The rest is set as default. Consequently, locate the cell tab, then select the cuvette type that was used for the experiment. For the calculation tab, you can select between monodisperse or polydisperse, and then the form of distribution can be adjusted depending on your choice. To save all the changes, select a location on the desktop where you will save the report file. Lastly, click on the Start Measurement to begin measuring. Once the measurement was finished, the result will then be displayed on your monitor, including the calculation data.
Maintenance and troubleshooting. To perform troubleshooting on the typical workflow, run the standard material and measure at least 3 repetitions. For hardware optimization, check the hardware conditions like concentration, particle support, dispersion, and duration. In concentration, measure at different percent transmittance and look at chi-square calculation. For the particle support, it must be high enough to suspend and circulate heavy particles but not so high that bubbles are introduced. In dispersion, investigate tails of distribution, check high end to see if agglomerates are removed, and check small end to see if new smaller particles appear. And lastly, for the duration, it can be simply automated in the software.
For its application,
Pharmaceutical industry. The tinier the particle is, the larger the occupied specific surface area, which tend for the particles to dissolve more quickly. In other words, the drug with a smaller volume will be metabolized in a quicker manner. In the case of microscopic components in medical injection, through the use of particle size analyzer, it allows the professionals to figure out how they pass through or penetrate capillaries and blood vessel walls, and which part of the body they reach. In monitoring of the behavior of the particles gives a major contribution on the efficacy and side effects of pharmaceutical products, wherein the pharmaceutical industry uses this information when designing a new drug. Nanoparticles technology. The study of nanoparticles technology nowadays create a wide range of benefits as a result of its special characteristics related to their sizes, wherein numerous prospective benefits for health and the environment are offered by nanotechnology. The particle size analyzer is used as an extremely important tool for developing methods to maintain good dispersion characteristics by ensuring contaminants and aggregates are identified and screened out. Cosmetic production. The test for the quality of cosmetic products, which includes moisturizer, facial powders, and lipsticks, are reliant on the determination of the amount of particles. Thus, the manufacturers use the particle size analyzer for the maintenance and quality control of this product. The difference in the color and shine together with the smoothness blocking properties of the product, such as creams, are controlled and dependent by the right particle size distribution.
For its application in the food products, the utilization of the particle size analyzer led into the molecule innovation that have been effectively applied into the food business. By controlling the particle size distribution in beverages, it gives an important role to ensure the consistent quality of it. Thus, the size dissemination of the particles can influence the taste, appearance, and steadiness, which will give a good end result for the food product. For soil engineering, the molecule size examination that measures by the particle size analyzer gives data on the size distribution of the particles. This data is basic in the soil and engineering enterprises to accomplish various objectives. This permits them to control the material fabricating condition and to accomplish a superior and a more secure and a more proficient materials. This particle size distribution of soil and cement has a large effect on the strength and stability of the supporting ground, wherein the testing of materials by a use of the particle size analyzer is the foundation of strength of building and other structure, and how much this changed over the long run after it was built.